Okay, let's start on our second topic in relation to the dynamic properties and theories and their implementation in engineering applications. After our week 3. So last week, in the end of the week, I think the intention was to let you know how we set up our equations of motions, right? How we're gonna set up the equations of motions. This week, we're gonna step another step forward, and we're gonna see how some of the details I'm gonna talk about to you today, they may be coming from basic information you may have been studied at university level, undergraduate level, and we're gonna see how things gonna go from there. If we had a section or a part not completed within the 2 hours, we may discuss it or talk or cover it during the workshops. So here we are, progressing with the skills you're supposed to be learning. And if we done this week, next week, 5 and 6, we're gonna have one topic which will run through 2 weeks. So after we learn what we have to learn this week, next week we will start dealing with forces applied on that single degree of freedom system. And the first force we're dealing with, or the first kind of dynamic action, it's harmonic excitation, which is simple, like as a sine or cosine motion. All right, it helps engineers a lot to evaluate the structures. So let's talk about today's topic, week number 4. We're gonna go through these sections. So I will talk quickly or remind you about undamped free vibration systems, how simple they are. Undamped free vibration, they are imaginary section, not real section, but we need to start from here to learn the basics and understand them. Then we're gonna get into systems which are still free vibrating. Yeah, you can see free vibration, free vibration, but now we're gonna see what's gonna happen to the equation of motion when we have damped systems. Not only equation of motion, we know that last week. We're gonna see how they will be graphed and their plots, or the time versus displacement graphs, and how the property is going to change. Number 3, type of damp. Now damped, it will lead us into 3 types of damped system. Damping, simply, it is stopping a system from vibration. The easiest way I can tell you what damping means, it's stopping a building from vibrating or shaking. There are, in engineering, there are 3 types. Civil engineers uses one of them. We're gonna see which one we use. Civil or structural engineers in buildings, we use one of them. We will know which one we use. Then after we're done with section 3, section 4, we're gonna go and look at the equation of motion we start looking at last week when it's applied on underdamped. So underdamped, I'm not saying not damped, I'm saying underdamped. Underdamped, it is the type that we use. So I just said to you here, I'm gonna introduce you to 3 types. The one that will be applied for buildings, it is underdamped, and you will see what does that mean and how it works. So in section 4 today, we're gonna see the equation of motion for the underdamped. Then when we're done with this, we're gonna do some practical situations or cases, why we need to learn all these kind of theories and how to practically implement them. One of its main usage is free vibration test. If you got a heritage building and you want to assess its dynamic properties to make reporting about its safety, etc., you would do free vibration tests, and we're going to see how we use such knowledge in doing such tests. If we had time today to finish this section, we will. Otherwise, we do it during the workshop. It is just one of the well-known damping methods is we use friction to create, to achieve damping, and we will do that. Okay, That's it. So I've got a question up here. Can we? I think I've given access. Week 3. Yeah, week 3 was recorded basically for Bendigo students. I think I've given permission if there were situations. So can you check your email? The students who emailed me, can you check your email? I trust you should have it now. I trust you should have it now, just for that question I had on the messages. Okay. So this is what we're doing today, and the key understanding points, dynamic properties, pay attention to it. You will practice it in examples. Free vibration tests, very useful, real practical tests engineers do for buildings and structures to determine those properties, because you can't hand calculate or theoretically find dynamic properties for built structures, because you may not know exactly what's the stiffness. You don't know the stiffness. You don't know maybe the concrete, the inertia, and which will help us to find K and all these parameters. And the last part here, damper friction, or friction dampers, which is one of the devices to create damping as we use a friction method. We will talk about this as well. So these are just this is just the table of contents which we will go through. So let us go back to where we stopped last week. We stopped at this equation of motion, which, as I said to you, it is a generic equation which tells us a system, a single degree of freedom system, which is having a mass m, and it's it's moving by a speed, u dot. Given that there is a speed involved, that means there is a damping, and this is the this is the stiffness, and there is an external excitation. The topic here is talking about undamped, not damped. So what does that mean? And also, sorry, there are two things here. First, undamped, right? Which reflects this going to be what? 0. This is undamped, not damped. And there is that wording which says free vibration. What does it mean, free vibration? It means the force here is 0. So what we're saying, starting from the very generic equation of motion, which is this, given that this section 4.1 is talking about undamped free vibrations, it means that the equation of motion will be as simple as you can see. As I said to you, these systems do not exist. In real buildings, you're always going to have some sort of damping, and you're always going to have some sort of excitation, which will cause the vibration, like earthquake or wind load. But we just want to look at it as simple as you can see here to understand some basics. So this is the equation of motion, right, which reflects and represents a system like this. Undamped free vibration. Okay, so now what we're trying to do here, we're just using math, which I do not want you to worry about in the subject. I just want you to understand how math is used to answer our engineering problems. Usually with these equations, one of the main aims for engineers is to find the displacement. We want to find motions. The word motion can be displacement, can be speed, can be acceleration. But one of the main ones we use, we find displacement. So we're gonna hire math and try to solve this equation and determine an equation that will define U for us. Analytically, how to do this? I think you studied it at math, whether school level or university level. Simply, this equation, it is, I think we said that to you. This is a differential equation, which is representing the free vibration systems. And if you remember, or you want to go to any math textbook, there is a process to do this. So what you're seeing here really is just a math business, which you won't be asked to do. We will not ask you to prove. So that's what I'm saying here in the notes. I'm saying to solve this second order differential equation, we have to apply some assumptions by giving initial conditions. So one of the initial conditions we're saying, initially when the time is 0, the displacement gonna be u, and the speed or velocity gonna be u dot. And then we're gonna go through some analytical math principles to solve that differential equation. And what you're going to end up with, this is the equation. This is the solution, which I will not ask you to do, but students who may like to look at it, they can look at the textbook that we are referencing as a recommended. You can look at it and see how they solve this homogeneous differential equation. Okay, so this is a homogeneous differential equation, second order. And the solution for it is as simple as you can see. That's it. So I don't want you to know more than this. You don't need to really memorize it or know the derivation process. So this basically represents this one. If you put this in an Excel, if you take this equation and put it in an Excel and change t, which is the time, from 0 to whatever, it will actually tell you, show you a curve like this, because that's how it's freely vibration. That's how a system will freely vibrate, like a sine or cosine, which you can see them here. Depends on where you're starting, whether you're starting from the top or from the 0, which gives you sine, or it will give you cosine if you like this. So it really doesn't matter. Now, when engineers come up with this equation, they said, now this equation, before they had the omega n, originally the k, because remember in the equation here we had k and m, right? So in the equation here, instead of omega n, they had this figure, root square k over m. Their engineers decided to call the stiffness over m, root square, as omega, which is what you all know from physics. It is the natural frequency. So this is the natural frequency of the system. Omega is the natural frequency of the system, which is defined by taking the root square k over m. From where it came from solving the equation. So basically, if you enjoy math and you want to solve this, you will end up finding this term is actually replaced by this one here. But then experimentally, it was found that this omega is kind of the natural frequency is defined by root square k over m, and that's why the equations and the engineers in this area, the vibrations, they always replace root square k over m by omega n. Okay, so let's agree about this definition. This is the first definition I'm trying to remind you. I'm sure you studied this at school or university, undergraduate level, but this is the omega value, which is the natural frequency. Do you know what is physically? Okay, I think it's explained here. Natural frequency, any system, any structure, any object standing in the world got its own natural frequency. If you stand up, you will have some sort of natural frequency. The spoon, any object, it's got its own natural frequency. And that natural frequency basically is calculated by taking root square stiffness. The stiffness of, even if a person is standing and stiffening up himself or herself, this is it. They're standing with open leg and they can withstand any vibration here, go left and right. Yet they stiffening up themselves, but they end up having their own natural frequency, like a building. Someone he's very strong and trying to balance him or herself very well. Their frequency can be low than a person who's very loose. He's not really ready for it. Look at it. This is how the building are. Some of them got very high natural frequency, very, very high natural frequency. That means they are, so look here at the equation. To have a high frequency, you need to have very high stiffness. Okay, whenever you increase frequency, you increase the stiffness, stiffer person, that means his frequency is very high. Whenever the mass goes high, the frequency goes low. So start to imagine these kind of parameters, not only just memorizing memorizing the formulas, because basically in these questions, yes, we can ask you to do something similar to the worked examples, which we share, something like this, which you like doing always, but there will always going to be a question that will be assessing your understanding to those parameters. So try to imagine those values, not only just say, give me the formula and I will try to rearrange. Okay, so coming back to what I'm trying to say here, this is the equation, yeah? If you use Excel to plot it by changing t from 0 to whatever, it will give you this function or this graph. But here what they did, they put some sort of value to the displacement. If you put displacement 0, it's going to start from here, and then it's just going to be, say, like that. So really it doesn't matter. Now, so what does this represent? This represents a system which is freely vibrating and no damp. So that means it is a structure which is going to be dancing forever or vibrating forever, which is not real. You always got some sort of internal friction. Even if there is no damping devices, they're going to be the friction between joints, whatever, going to take things down. Okay. So that's why I'm saying it's not real, but it just helps us to teach you these kind of properties. And also try to, people, if they still don't understand, this is a graph, but for a real single degree of freedom system, this is a frame. At point A, yeah, at time A, this is the situation. It is at the no displaced position. So we are at the original location, right? Then when the system goes from A to B, okay, that means it's going to amplitude. So you can see they reached the maximum displacement towards the right. And that's here you can see you got the displacement here, which is there as well. So this is the maximum amplitude, which is here giving to you, U dot or UO. Then when it goes down to C, we're going to be here, back to 0. Then when it goes to D, it's going to be almost as far as it can to the left. Then when it's going to go. This is vibration, which you all know, but what you need to remember, and which you did study this before, as I said, or you need to know, from here to there, it is one cycle. It is a one cycle for the object to travel. All right, don't get confused from here, because some people think from there coming back to the same point is a cycle. No, this is half a cycle. A cycle is starting from A all the way to E. Now, so we agree, the cycle for a system, it is the full vibration from no vibration or the original status, then peaking up to the left, to the right, coming back to the 0 displacement, then peaking up to the left, then coming back. This is a full cycle. Now, this full cycle gives us some important information. It gives you the natural time period. Natural time period. As I said, there is first thing we talked about, there is a natural frequency, which is a vibration. How many, the natural, we're going to have a clear definitions. The natural frequency, it's how many cycles we did in a particular time. The time period, the natural time is the actual seconds, the actual time it takes the system to go from A to E. So we're talking here about time, whether it's 1 second, half a second, to a second, and you all practiced things with your assignments, and you've all, I trust, have been calculating your natural frequencies for your building as per the standard. So this is the natural frequency you calculated. It was also called a T. It is actually the time it will take the building to travel from no earthquake, from static all the way to the left, then to all the way to the right, then comes back to 0. That's the natural frequency. Sorry, the time period, the seconds. Now, yeah, if you apply this formula, you will be able to find the natural frequency. So from the slide, just try to remember what's the T and the natural time period is, and the natural frequency is, and understand the actual meaning of such parameters. So this slide basically is kind of confirming what we talked about before. Yeah, just know carefully what the natural period of vibration is, which is Tn, which I talked to you already about, and the omega, it is the natural circular frequency of vibration. Someone can ask me why we need to be bothered about knowing them. This parameter here, it's one of the critical ones to tell us. Today, we're not talking about actions, or this week, we're not talking about actions coming to the structure. We're talking about the behavior of the building itself. Okay, so a natural frequency or time or natural time period for a structure is a property for a structure and depends on how strong it is, how heavy it is, the framing arrangement. Okay, so if I know this parameter, and next week I'm going to know the forced frequency. So next week we're going to be talking about frequency and omega again, but it's going to be the forced one. Forced one, that means it's coming from outside, from earthquake or whatever. We need to make sure this natural frequency is not close to the forced frequency. If it was same, what's going to happen? Anyone knows or remember? When this frequency going to be same as the buildings, when this frequency, which is the building frequency, if it's very close or same as the forcing frequency from harmonic motion, for example, what's going to happen to the building? You remember that from physics?
Like resonance, going to vibrate.
Excellent. That's the word. Yeah, resonance. That's it. So that will make the problem. And this is what we want to avoid in dynamics. I think that's the main aim of this, is you need to know a lot of things to make sure the frequencies don't come together. How? As an engineer, how to do this? By, if you found it's happening, then your building is sensitive. Then you have to think about doing something to the building. Go make your stiffness higher, right? And that will change your frequency here and then. You cannot control what's coming from outside. If it was earthquake, you can control the building itself. So they change this. Maybe we cannot change the mass of the building. You remember in New Zealand, many, I think it was 10 years or 7 years ago, they had a major earthquake in Christchurch. And I think what they aimed to do there, the whole city almost, there was a big damage in many buildings, and the newly developed buildings were all based on timber. So they changed the mass, all their new structures, and they start researching a lot into timber, because basically they're changing the frequency. They want to change the frequency. Okay, but if you're talking about existing building and towers, this is difficult to change. It needs to be concrete, so you can change stiffness by making, or as you're going to see next week, we can play with damping. Damping can help us to control as well. So that's really the main message of what you're doing, not only today, over the many weeks or most of the weeks we're working on. So quick definitions here again. This guy, omega, it's called what? Natural frequency. Natural, just pay attention to this wording. You know, some people say frequency, but they sometimes get confused. Is this the omega or F? I'm sure some of you have read it F, some of you have read it omega. They are different in terms of the units, I would say, or the physical meaning. This is a circular frequency, okay? But it's like kind of using angles in its formula. But this one, it is a cycle. Cycle means how many cycles per second is completed. But this one, it is a circular frequency, like you see inside the equations or inside the formula, you got the pi, the angles. So that's basically the difference. And in case you're using this, you just need to kind of use the correct units. Just understand frequency sometimes may be the circular frequency, or it may be the cycle frequency. If it's cycle frequency, then it is just the inverse of the natural time period. But if we're talking about circular frequency, it's gonna be in function. It's not only the inverse, you have to have it in function of pi. Okay, so just in case students get a bit mixed up, and eventually there is a relationship between the cycle frequency and the circular frequency by using 2 pi. So very, basic things. I'm sure you've used them definitely in the past, being master students, and just try to remember these kind of properties and relationships, because we're going to be using them more and more. So in summary of what I've talked about, I'm still in section 1.1 or 4.1, and I'm still talking about this unreal, undamped free vibration system. We have 3 properties to kind of know about. One of them is the circular natural frequency, natural time period, and cycle natural frequency. So you have them there. Now, before we leave this section or this section here, I just want you to imagine things more. One of them here is stiffer of 2 single degree of freedom systems having the same mass will have higher natural frequency. Okay, so imagine you have 2 systems. Let me just draw a small. You've got 2 systems. I'm drawing a single degree of freedom, so they have the same mass. You've got 2 systems with the same mass. Yeah, same mass will have. Okay, what we're saying here, if one of them got a stiffer column, so you see here we've got a thicker or stiffer column. All right, which one will have higher natural frequency, A or B? So the answer is in front of you. Yeah, so A in this case, because it's stiffer, it will have higher natural frequency and shorter natural period. Obviously, it's vibration. So if I will just draw it in red as well. So it will have higher natural frequency. So its frequency will be very kind of condensed, very condensed. Okay. Now, if we, this one here, but the B, number B, I'll make it in green, number B, it will have kind of more frequency, larger, smaller frequency, and larger time period. So again, the time period goes from here all the way to there. So you can see the green one. The green one represents what's happening with B. It can sway a lot left and right. So it has actually longer time period. Its natural time period takes long time to happen. Okay, and it has less frequency. But number A, which is a stiffer, it's got higher natural frequency, and it's got shorter natural period. You can see here its natural period is much, much shorter because it's stiffer. Okay? So just try to imagine always what each system means. And as a reverse situation for what we said above, if we have the same stiffnesses, so same stiffnesses for a system, and one of the system is heavier than the other, so the masses are different, one small and one big, and try to imagine what's going to happen to the system. And we're saying they have the same columns, the same stiffnesses, right? So it's saying the heavier, more mass of 2 structures having the same stiffness will have lower natural frequency. So same concept and longer time period. All right, the one which is heavy, it will take more time to sway, right? And it will have longer time period because it's heavy. But the one which is lighter with the same stiffness as per the previous one will have higher frequency. And so make sure you understand that, because it's going to help you to answer those practical questions. Okay, the last slide, which talks about undamped vibration. It is nothing new. We're just saying in case we need to have. So we're just replacing those equations. You know, we said before, the static displacement, yeah, static displacement equals to mass G over the stiffness. So we simply replacing here the formula. So these three examples, because they may be used in some of our mocked examples. So what we're saying, the natural cycle circular frequency or natural cycle frequency or natural time period, they can also be defined with different parameters, not only stiffness over, and because the stiffness can be replaced by the static displacement. Okay, stiffness can be related to the static displacement when multiplied by S. This simply comes from what we all know. Yeah. This one here, remember, it is just the acceleration. Mass times acceleration is a force. So if you want to remember, force over K, yeah. So mass times gravity will give us force. And we all know if we divide force over stiffness will give us displacement, static displacement. We said that last week as well. So, or if you remember, stiffness comes from, yeah, force over displacement, delta. So we're kind of using the same thing, nothing new. In case we are chasing static deformation. So we just want to show you this in the notes as it may be employed in some of the problems. Okay, now some examples for real kind of buildings. In this building, you can see here, they're giving us information about the time period. So this is a time period. If I now say this is the long direction, the L, and the red here is the short direction, S. Can someone tell me 1.67 second time period? Is it okay? I'm trying to say which one is the north-south. Hopefully the answer is not there. But which one gonna vibrate? Or 1.67, is it happening along S or along L? The 1.6 second time period. So which one you think is gonna take shorter time to vibrate? Is it along the S or along the L? Again, we're looking at this number. This building you see in front of you, it is reported, it is 26-story development. Just use my laser thing. 26-story steel building. They're saying that its time period, Tn, is 1.67 seconds for the north-south. So what I'm asking you, where do you think the north-south direction is? Is it the S, the short, or the long?
For S, because stiffness will be less along S.
Thanks for trying to answer, but let's think about it. What you're saying to me, 1.6, it's actually along the short, right? When stiffness, which as you said, it is less, the stiffness is less. Now, when the stiffness reduces, let's go back to this equation. When the stiffness reduces, maybe it's better to look at the T equation, which is here. Or look, maybe let's look here first. When the stiffness decreases, this will decrease, right? When this will decrease, what's going to happen to T will increase. But you have to look at this direction as well. This has a higher time period. They're saying that it's got 2.2 second east-west. So that means the higher time period should be in the short direction. So do you still agree with what you said, or what you think?
No, got it, sir.
You got it. Yeah. So to clarify a bit more for you, this direction is actually it's, you know, always I like to imagine the building where it's going to be swaying softly and more. This, you can see this is the shortest direction, so it should have the higher time period. So this is actually the east-west. East-west. The east-west direction is in this one. Okay. And along the blue, the green color here, this is the north-south. This is the north-south because that's the stiffer direction. The building, when it's when the building vibrates along L, it will be stronger. So just imagine it's going to be vibrating with a lot of frequency and smaller time period. So if I try to graph the displacement versus time, say the frequency will be something like this in this green direction, kind of. But if I graph the red for you, yeah, you would expect it to be kind of more. I'm trying to use my mouse, so just bear with me. Yeah, this is it here. So you can see here the time period is longer and it has less frequency. Frequency means how many cycles or circles are there. It has less. Here we got more with the green, and you can see the time period is small. So that's basically, you need to imagine these numbers. What does it really mean? And obviously, which side will be sensitive for you? Which one will be more sensitive for you to worry about? Obviously, the short one, because the building will be more sensitive. Any question before I delete it? Another building. This building, you can see it's a square. It's got only, it does not have no south, north, east, west. They gave us only one value, which is 3 seconds. Obviously, it's taller. It's taller than this one. This was only 26. This one is 50 floors. So again, whenever you go higher, you will have it kind of more, it will need more time to finish its cycle. So you see it's here, we're talking about 2.9 seconds frequency. Okay. Let's see another quick example, a bridge. A bridge is more complicated. Here with the bridges, engineers need to look at many different directions. Here we're looking at the transverse direction, where, because with such system, we have to look to the vibration in this direction as well, like in the plan. And so they have it as 18.2 vertical. Let me use green. So the green 18.2 is flat, right? Horizontal vibration, and the vertical vibration, which is about 11-second time period. It is vertical. You've got longitudinal vibrations. Also, we need to look at vibrations, which is blue, that will show you how sensitive is the bridges are, right? The towers, sorry. It's got even less. And sometimes we can look at, sorry, it was yellow, should be yellow or orange. And on top of that, they look, because it's quite skinny, elements inside it. They also do, and definitely they would use some of those packages. They can't use equations, the ones we discussed, unless they simplify it, and try to use those equations. So the blue one represents the torsion. So they also look at the torsion behavior. But just the point is, you just need to sense those numbers. Yeah, we're talking here about seconds. We're not talking about minutes for the cycle to finish. So it's not really. The last one was just the twisting for the structure or the tower, just to consider and check everything from wind or traffic, whatever they want to look at. Very last one, this structure is giving us 3.57 seconds, and you can see many structures, heritage structures like this in Melbourne as well, where people report about. And today, one of the tasks going to show you how you can use free vibration tests to determine such value. Because say this was built, about 50 or 100 years ago, and after an earthquake or after 10 years, the council want to check its performance. One of the things you need to look at is the stiffness of that structure. You can't do it by hand because you don't know where are the cracks. You don't know if there is a little crack here somewhere, that will change. You cannot just go and use formulas to find K, because you're not sure if it's, you can do it by hand, and then this is going to tell you what the K going to be, but we don't know if this is the true. So how to make sure? We have to do a test, because it's going to tell you what's the actual K. If you found the actual K is way, way, way below what the ideal non-damaged section is, then you can say to council, be careful. The test showed us the stiffness is way, way less than expected. So that's really how it works. Questions? Now, before we're still here at section, so see this, that's the reason why we looked at this unreal case. It just teaches us many properties and let us understand them. Some minor properties you need to know about these systems. Usually this part is called amplitude, the maximum displacement or sway that single degree of freedom system reached. It's typically calculated by this equation, which we may use at some stage in our calculations as well. Okay, so just know where they live in your, now just to let you know, in your final exams, it's not a textbook, it's not an open book exam, but you will be allowed to bring 1 page sheet, 1 or 2, I will confirm that later. You will be allowed to bring 1 page or 2 to write notes on it. Okay, that's for your, just to let you know, so you can consider when you study this subject. So that's the maximum amplitude can be calculated from here, and the maximum acceleration can be calculated as well from these formulas. They're kind of analytically driven. If you want to know how, they are clearly available in the textbook. But this subject is not asking you to do that. I just want you to know how to practice things, engineering application. Example 1. This is very simple example, and it is a continuation for what you did last week. So last week we talked about this structure, single degree of freedom warehouse with 1 roof, and last week you've worked with me and you did the equation of motion. We did together the equation of motion, whether along the north, south, east direction or the east-west direction. So look at what we did last week, week 3, example 3.2. We have worked out together and we have written the equation of motions for both directions. What we want to do today is to determine the natural cycle frequency, the natural circle frequency and cycle frequency and time period for those directions. That's all. Okay. Let's see how we do them. All right. So the solution, you all have it. And basically, last week, if you remember, we've calculated these things. Last week, we've calculated the chem, K, the stiffness, and M along the north-south direction or east-west direction. So I don't need to do it for you. You know, here it's really very easy step. Then for you, if this was all done already from last week, you have almost nothing. The circular frequency, omega n, is simply just substitute these two parameters directly into the formula, which I told you where it lives, and all good. So the north-south natural circular frequency is 28 radian. See the unit here? When we're talking about cycle frequency, we're talking with these units, radian per second. When we're talking about circular frequency, we're going to be talking about hertz, because hertz means how many cycles per second. That's what hertz means, is how many cycles per second. Okay, so the answer for north-south direction, the answer is 28 radian per second, and for the circular frequency, it is about 4.5 hertz. The time period, simply you can either take the inverse of this value. So it really doesn't matter which one you want to do first. You can do them in any order, but typically you would start with the natural circular frequency. Circular frequency, you should start with this because it helps you to go to the others. But it doesn't matter whether you calculate this first or that first. All right, so here are the answers. And looking to the east-west direction, yeah, which was this one. Short direction, if you remember last week, which was in control of the bracing rods, then you should be able to find the omega, the circular frequency 52, and see, it's stiffer. See, it's stiffer. If you compare the short direction with the long direction, compare these two values, it's kind of double. Right? It is basically double. Okay, that's because the north-south was kind of more wobbly, if you like, because the stiffness is basically smaller. It was only dependent on what? On the columns. You remember, the columns will only the members who resist lateral load. But in the short direction, we had those X bracing, and they gave us a lot of much more powerful resistance. And you can see how the frequency get higher, and it will control the vibrations more. And the time period again get smaller, the time period. So this is kind of an engineering. If you have a structure, and it's not only about earthquake, it's maybe this is a very sensitive structure with a lot of glass, okay? And the client came to you and say, I hear a lot of noise when the tram. See, this is how they do these things when a tram or a bus or whatever moves next to that building. What should I do? Just find members to input. Maybe you just need to put members like this that will. So what's happening without them? Let's say this was not there. The problem was the resonance, which one of you already mentioned. If you have a car or a truck moving in front of your house and it's kind of shaking the floor or making a lot of noise with a structure like this, the solution basically is just stiffen it up a bit. When you're going to stiffen it up, you're going to change its frequency, natural frequency. You're going to amplify the natural frequency. And that's it. It's going to solve the problem. Okay. Any question about this question? Did you manage, Sah, to find the link? Raj. All right, no question. You are ready to any type of questions in the final exam? If yes, then all good. Okay, so now we're going to go to section 4.2. What do we have here? Damping. So we're still talking about free vibration. Nothing new. It's still free vibration. Okay, but the new thing, so nothing new about the move, no internal external forces happening to the structure. We just have damping in business, and simply let's see what's going to happen to the equation. The equation will look something like this, right? So still we got 0 because no external, we got 0 here because no external actions, and we have the damping introduced in the equation. So all good so far. So from math, we want to just kind of manipulate and rearrange things. So what we did here, we said we're going to divide over mass, which is fine. So the mass is gone, this is gone, okay? And if you divide K over mass, you will be able to replace K over M by omega squared. Yeah, that's simply just from the definition of omega. That's simply just from the definition of omega. Okay, nothing really different or special. Then what's happening here? We're going to have this kind of arrangement of parameters or properties, which is maybe new for you because we're here talking about damping. So after we divide the C over M, engineers came up with different definitions. Okay, so they said the C, basically it is in function of omega, so they can basically replace the C with 2 eta by omega natural frequency. Now, given that omega is equal to K over M, right? So originally, again, to simplify it for you, originally this was in the equation, okay? And C is actually a function of the damping, okay? Now, to simplify things even more, this one is actually defined as you can see. So that's how the equation, if you, as I said, if you enjoy math and you would like to solve this, you will be able to come up with the term here will be kind of exploded to have this and have this inside it. But engineers have simplified it in a way where they called this ratio. So they took out this ratio and called another parameter called eta, which I will tell you. It is the damping ratio. This is called the damping ratio. And this is, by the way, it's called the damping constant. Okay, which is the damping ratio can be defined as the ratio between the damping constant of the system over critical damping, where critical damping comes from multiplying 2 by the mass by the natural frequency of the system. Okay, so if someone wants to know how this we divided over M and how we jumped from C over M to there, these are basically coming from deviation processes, which again, I don't want you to worry about. You just need to know the original reflection, which means what eta means and how it's defined by this formula, which we're going to be applying and using in our solutions. And this one we talked about already previously when we had free vibration, no damping. Now, so based on what you see here, the critical damping, which I will tell you what it is later when we see other graphs, is equal to 2m omega, natural omega, which is already given to us here. And we know that this can be replaced by involving the stiffness and mass. So if you look at, again, algebra inside there, you're going to see we can end up with this definition. Yeah, we just replace omega by root square k over m, and then we squared up this m inside the root, and we ended up with this arrangement. So it's not really complicated. Then we can say also we can define critical damping by this figure. So what we're trying to show you here, really, the summary of these kind of formulations is the critical damping have different ways to be reflected by, or different definitions or different relationships to use. It doesn't matter which one we use, depends on our problem and what we are given. Then you can decide on the shortest way to select the right relationship. All right, so again, this is our equation of motion, which reflects a damped system and still vibrating freely, no issues. Now, let's go to the next slide and see some definitions, which I've already mentioned to you, but quickly going through them. CR, it is defined as the critical damping. You don't know at this stage practically what does it mean. I'll explain that to you next. Critical damping, it is a point where something gonna happen, or the system will be separating two different conditions, which I will come to later on. Okay. Damping constancy, it depends on the, if we're talking about a device that it was done by mechanical engineers, you know, those Pitstone, the damping systems, or like the damping systems in your car, suspension system in your car. This is basically a damping system which has its own value. So the mechanical engineers who are going to manufacture this suspension system, they will tell you what C is. It depends on the fluid inside it, whatever it is, air or fluid or whatever it is. Okay, so it is just a typically given material, constant material. The last parameter here, eta, it is the damping ratio, or the fraction of critical damping, which is simply, if you look at the formula, is dividing the C over the critical C, which I will tell you about shortly. So these are just the definitions for the three parameter. And let's use math. So what we're saying here is we're going to go to this equation and try to solve it. So this is it here, equation number 1. Equation number 2, I've just copied these two equations from the previous slide here. Nothing new. All right, equation number 1, equation number 2, we all know about. Then what they found, actually, they found the solutions for this equation can have 3 options. Okay, we can have 3 options depending on where the damping ratio sits. They have 3 options or 3 types. The first one, if let's talk about the critical damp system, when this is equal to that. Okay, so we said there is a critical damping value when the C is equal to CCR, which is the critical damping. That's why we call it the critical damping, because the CCR is basically same as C. If we are in this situation, then they found the equation can be solved and it will give us a curve like the one I'm highlighting. What does this practically mean? It means that if you disturb a system, right, and you release it, whether you loaded it or you displaced it, then you released it to vibrate, it will go to 0 straight away. So it's unlike what I mentioned to you here, or I remember what I showed you here with the free vibration, where the system gonna go to the left and right and all that. No, in this case, it's gonna go from the peak all the way to here and stops. That's it. So it's just gonna go from this situation to here. It will not move more because the damping shuts it down, and that's why they call it. It is critical damping. So it won't vibrate. If you have this level of damping in your system, it's gonna shut it down straight away. Now, over damped, you can have even more softer shock. So in case, just to let you know from now, this case, the critical damped and over damped, they nothing to do with structural engineers. You cannot do this for a building. It's too much. You can do this for small mechanical equipment, which mechanical engineers can do in a factory or any mechanical, like robots or whatever they're designing. They can do this there, or in a vehicle, they can do this, but not for buildings. All right. Now, sometimes traffic engineer would like to think about using such mechanism because, you know, when, you know, the road barriers, not sure if I'm able to show you a picture here. Okay, here we go. I think most of you have seen these things, which I will share with you. Just give me a second. They got ones which no, not here. So, you know, there's sometimes shock absorbers at the front. Let me just show you, because that's where sometimes, oh, you see this one? This is the one I'm trying to see, but I couldn't see it in the picture. You know, you've got these kind of rubber-based. Usually when those are designed, the traffic engineers, who are also civil engineers, they're gonna aim at having this level of damping, this one, the soft one, the over damped. Yeah, because when a vehicle hits it, they want to actually let the vehicle stay here. They don't want, oh, what did I do? Yeah, that's better. Okay, yeah, that helps. Ah, perfect. This is the one I wanted to show you. So, okay, when they design these things, they actually want to absorb all the energy from the vehicles and try to keep it away from the road when a vehicle hits it. So this is kind of a damping elements when a vehicle hits it. Right, that's where civil engineers will be thinking about going to over damped situations. Okay, because they actually don't want the car to bounce back to the road and make another accident. They just want to keep it there. So they want to absorb all the shock. And to achieve such thing mathematically, and what we are doing, it is basically something like what we're talking about here. You have to design your system in a way. So basically, as a designer, you will aim at designing your system in a way where your C value will be more than the critical C, which you can calculate by the weight of the car and the frequency, whatever you can consider there. So because the car will have its own stiffness, whatever, and you can do this by simulations, whatever they do as a traffic designers. So that's really how it works. So what I was trying to tell you, this equation, when people solved it, they found it can have up to 3 solutions. Okay, and one of them is a curve like this, which gonna happen when C is equal to C critical. Another one, it's like this, when C is more than C critical, which I said civil engineers for buildings will never be there because you can't have a building like this. Otherwise, your building gonna be without windows. It's just gonna be, even if you had it all concrete, it's still gonna shake a bit. You can't really have it. All right, needs to be very, very short and full of concrete, which nobody will get there. This is the one for civil structural engineers. That's it. That's how they build it. So yes, there is damping, but after several few cycles, the motion or vibration will go away, and that's what we always aim at. We should have some damping, and that damping should be under damped. So what does it mean mathematically or by numbers? Your damping ratio is less than 1. When your damping ratio is less than 1, then that means you can have such function or such graph, and that's really the situation we live in. So I'm talking mathematically. If you really go and try to solve this, you're going to find 3 complicated solutions. I'll show you one of them how it is. So type 1, it is, as I said, it is when C less than C critical, which is the type we work with in structural engineering. Type 2, it is when the critical is equal to, when the damping constant is equal to critical damping, which means damping ratio is 1, and that means the system returns to its equilibrium straight away without vibration. It will straight away return. Also, this case here, it will return, but with a slower rate, where I would say civil engineers think about this for systems such as this. They don't want, again, to hurt the people inside the car. They don't want like to make something very, very strong that will hurt the people. They want just to absorb the shock. But anyway, they may pay for fixing it again. So that's it. This is the solution we're going to go with. So let's see the next slide here. So basically, this slide just repeats what I was talking to you about. We do have 3 solutions, and this one, it is the solution that we will focus. All of them are applicable solutions, remember. But for what we're teaching you in the subject, this is going to be the type we are interested in. And if we solve it now, so this page here is just giving you that's, we, as I said here, the lecture will be restricted to what? Under-damped systems. Yeah, under-damped systems for reasons you know. When C is equal to C, because structures of interest like buildings, bridges, dams, whatever we're talking about, they are typically within this range. Okay, they are typically within this range, 0.1 damping ratio. Even, as I said, for buildings which has no damping element like device, we can assume it to have 0.05% damping. Okay. Therefore, we will have little reason to study dynamics for critically damped systems or over-damped systems. We won't be studying these situations because it's not something we will practice in real situations, apart or if you're going to be working with as a traffic engineer and want to design these things here. So now we're going to continue the solution. Okay, we're going to assume we have this type of damping, and we're going to continue the solution, which I put it again for you here. But again, I don't want you to worry about the math business. And I jumped from, so this is equation 1 and 2 are repeated from before. Equation number 3 are the conditions, which we have to use to solve our homogeneous differential equation. Then here is the solution. See how complicated it is. This is the solution. Okay, that's it. That's the solution, and this is when our damping constant is less than critical damping. Now, let's graph it. Before we graph it, I just want you to, the systems we're talking about are under-damped. And remember, we were talking about free vibration with damping. So in case, to understand the kind of proof it, if you, for instance, have substituted the damping ratio with 0, like you want to say this equation can be applicable for no damping systems, and you substituted the damping ratio by 0, you will end up finding what? You will end up finding this equation, which was the solution for the free vibration, no damping. So this is the equation I showed you before, equation number 5. So this equation, it is same equation I showed you in slide 5, which was the solution we had for the free vibration, no damping case. Okay, this is just kind of proof telling you that this is a valid or correct solution, because if you simply put 0 for the damping ratio, then you will end up with this solution, and all good. Okay, so that's about the equation. So again, this is our equation, and if you plot this equation in Excel for a specific value of damping ratio over particular time, this is what you're gonna get. You're gonna get this kind of dark solid line. This is the solution. So this is if you specified 5% damping, yeah, if you had your damping ratio as 0.05, which is inside here, 0.05, and you keep changing T over time in your Excel file, and you try to plot it with Excel, you will have this thick line. That's it, which really gives you a good sense about how damped structures looks like, okay, or how they vibrate over time. And this is displacement. And they compared it with undamped structure. So the thin line, it is undamped, and the thick line, it is damped structure. So you can sense the differences. And again, the equation they used to plot it is here, which we solved. Complicated one. Remember, the damp type here is under damped. Okay. One thing to pay attention to, for the thick line, which is for damped structures, we're gonna have a special frequency. So when you see omega capital D, that means it is still the natural frequency for damped structures, okay? And from the formulation, it can be equal to the original natural frequency of the system multiplied by this root square function, which is, as you can see, in function of the damping ratio. So yes, the damping ratio will have, which we assumed here it is only 5%. Yes, the damping ratio will have an impact on the frequency. It's not only going to stop the vibration, it will also have a slight impact, you can see here the differences. See what's happened to the natural time period. This is a natural time period, right? And here you have your natural damped time period. So things will change slightly, and by using this function, and we're going to see as well the other functions which let us determine the time period, the damped time period as well. Okay, so in this section, we're talking about the equation of motion for underdamped systems, for the situation where we have free vibration and we have damping systems, right? Now, again, the natural period as well of the vibration, it's not only about the frequency, we can also calculate the damped natural period, right? Which simply comes from dividing the actual original natural time period over this root square, which, as you can see, again, it's a function of the damping ratio, and you can compare the differences as well. All right, what else we need to know? So there are some kind of features and parameters. Really, what you're collecting today is parameters. You need to know physically what they mean. You need to know where are the formulas. You don't need to memorize them. You're going to have sheet to write your formulas on, but they will be used in our problem solving questions. So the other useful property we're going to be using as well to solve real problems is the decay of amplitudes. Yeah, we call this from free vibration, this displacement, we call it amplitude. Yeah, we call it amplitude, and we have a formula for it. Now, this amplitude is decaying over time. So from math, engineers were able to determine the formula for this, which is, as you can see here. Okay, so there is a formula. We may or may not use it in our problem. So you just need to know where is it in our sheets, in our document. So you see how the decay, maybe for us as a civil engineers, it's not really a problem. We always need to worry what's going to happen here. And then we're going to think about, I would really be interested to see the worst case scenario. But How it's going to be decaying, maybe it's not that practically important for us, but maybe important for other. Maybe, you know, that's true, the traffic engineering problem, it may be more useful in case they couldn't achieve that critical damping or over critical damping status. So if we really want to see how the peak is reducing over time, we can employ this analytically driven equation, and rho here is simply coming from this. So again, setting up those equations takes pages of pages, and you can't simply see them from textbooks. They will tell you how they're all driven by math, but you don't need to know that. You don't need to show that to us. You just need to know, if you've been asked in some of the questions about calculating the reduction in amplitudes, you know how to do it because you've got the equations to do that. Okay, we still have special feature. We have special feature about underdamped systems. Okay, what does it say here? It is, what do they found? Have a look to this graph. The horizontal axis, it is the damping ratio, okay, starting from 0. The vertical one, it is the ratio between damped and natural undamped systems. So you can see the vertical axis represent ratios, whether circular frequencies or time periods. Okay, so here we're dividing the damped over natural for the frequencies, or we're dividing the time, the natural over damped for the time, because you know it's reversed. So regardless which parameters we have and which parameters to use, you just need to understand what's happening. At the start, see at the start, when we have no damping and up to 20% damping, we found that what's happening to, is there a major difference between damped and undamped in terms of frequency and time period? The answer is no. The answer is no. You can see it's almost flat. So what does this mean? It means that there is no major difference between damped or undamped frequencies or time periods, natural time periods, right? And this is happening mostly within this range. The good news is, typically, most of your buildings will not be damped more than 20%. It's a lot. In structures, right? We usually, as I said, in buildings, like most of buildings in Melbourne, they don't have special damping features. We're just gonna use the connections, the concrete properties, which got all the micro cracks, whatever. And ideally, this will give you 5% damping. If for high-rise building, they start introducing things, they may start having up to 10. So what we're saying here, and as we said, even in some of the notes before, we said usually buildings are, what did we say here in these notes to you? If you remember these notes, yeah? Usually for buildings is less than what, 10%. So what does that mean? We actually, in this graph, where do we sit? We sit somewhere here. So that's really gives civil structure engineers a good message, is don't need to worry about the differences between damped or not damped frequencies or damped or not damped time periods, which is good news, folks. That's basically what we can learn from this exercise. Okay, so someone have plotted this curve, which is simply he just redo this equation, this one. He just plotted it in Excel for different damping ratio values and different frequencies and time periods, and then they ended up plotting it like that, and it gave us a very good summary and conclusion that it is really not changing much, which is giving us a good message. This slide here let you imagine and explain, imagine and understand, imagine and understand how damping can change the look of vibration. So if we have, for example, 2%, this is what's going to happen to your building. If you've got 5% more damping, which I said typically for buildings in Melbourne, we would go with this. That's what can happen. Yeah. 10%, you can shut the vibration quicker. 20%, very, very quick. So you see, and this is too much to get. You can't get 20% damping, only if you had special devices like the one I showed you. And if you remember last week, you got like pistons or special devices to fix inside your building. Right, so any questions about this section, like under damped systems? Do we all understand this was simply one type of damping, and which we widely use in structures? And I think you've understood what's happening between them. Any questions there? Okay, section 5, free vibration. This is what I'm talking to you here about real application for the knowledge we talked about. So free vibration test is a real application for dynamic engineers to employ and apply in answering real questions by using the theories we talked about. So because it's not possible to determine analytically damping ratios for practical structures. Yeah, if you got a building which was built 50, 60 years ago, you can't rely on, even if you have their original structural drawings, you can't assume all the columns are intact, or maybe the columns, you know, over time when the concrete ages, it gets stronger. So maybe even it's getting stronger. So you can't just assume the concrete stays as it is. And another scenarios is after an earthquake or any disaster. Council will try to go and check the buildings, some particular buildings. Then again, you can't rely then on the structural drawings because maybe some of the columns are damaged. You can't see the damage, maybe some internal cracks there. So what we do is we do tests, okay? Then it should be determined what experimentally, that's what we're talking about. So what we do, free vibration tests, which means we're going to be pre-disturbing a structure, then recording its vibration. So simply what we're doing, we're going to be pre-disturbing a structure, right? Sometimes we can pre-disturb it on a shake table test, but this is for experiments like that, okay? We can't do this for a building. We cannot shake a building. We cannot put a building on a table and shake it. All right. Well, this was just a simple example. Now for real structures, I'll tell you what we can do. We can pre-displace it for several millimeters and then release it to vibrate. So, but basically what we are doing, we're trying to pre-disturb the structure, whether by acceleration or velocity. Then we're going to be recording the response, whether acceleration or displacement. And then what we're going to do, we're going to answer our questions by using the formulas we showed you. Whether you can find the frequency, the damping frequency, you can find the natural frequency, the natural time period, etc. So, and again, you should be able to work out backwards the stiffness and the mass and whatever you want. And that's the fun about it, you know. And that will let you make a judgment if that building is good or not. So again, part of the previous vibration record. So again, this formula I think we looked at, but again, one of the formulas driven that will tell us what's happening with the damping ratio. So to calculate the damping ratio based on the amplitudes, yeah, we are able to use this relationship, whether in function of displacement or in function of acceleration, which is what we really want. So based on the formulas we showed you, remember that complicated one, which I showed you, it's a function of rho. It can be readjusted in a way which is shown in the textbook. You don't need to show me that in this subject, but you just need to know about using this. Just need to know about using this and know how to apply it. So we are able to relate between the damping ratio and the displacement amplitudes, which we are talking about. And we're going to see that in an example. Okay, so from there, we can determine the time, the damped time period. And basically, then you can compare what you calculated with the original calculated stiffness and then make a judgment whether it's safe or not safe. Because as I said in the council, after a disaster or whatever, you will have the original structural drawings and calculate the stiffness. And it will give you, from the stiffness, you will calculate the actual vibrations or properties. Then you're going to do experiments, and the experiment will tell you the tested frequencies, and you're going to compare. If they are same, that means the building's still intact. If different, then there is some damages, and you can determine whether it's getting weaker or stronger. If it's stronger, that means it was just aging concrete, which you know, with time, the concrete gets stronger. So that means it's good anyway. So here is an example, very simple start for an example, which is asking you to determine the natural vibration period and damping ratio, okay, for this system. So we're not talking about the buildings for now, we're just talking about this simplified system. Okay. So they got these plastic-based or metal-based frames. And I think the one we're looking at is the plexiglass. So this one, this is what we're looking at. Okay. So they have it fixed on top of the shake table, and they pre-disturbed it, and then they stopped the vibration. See, they pre-disturbed it, then they stopped the vibration, then the frame started to vibrate as shown here with these amplitudes. So you did this test. It's only going to take from you about 8 seconds. That's it. So it's just a test. Gonna click, gonna vibrate. You need to set up all your displacement and this is what we call an acceleration sensor. This one measures acceleration. So you just like it's got a magnet. You connect it to the side here, or glue it, or do whatever. Right? It's gonna measure the acceleration. They have these accelerations in the vehicles. You know, if you got that, they call that thing which pops out from the steering. Got the name. So you got these kind of sensors. Most of all the vehicles got it. If you got this thing which pops out of the steering, the airbags. Okay, the airbags, they will be triggered and they will start in case they got very strong acceleration. That means there is an accident. They will pop out to the passenger or to the driver. So same as those devices, you will attach it here, and then you're going to do your test for 10 seconds or 8 seconds, and it will give you these records. Done? And that's it. You can then solve for answers. Simply, as you can see, answering the first question, what did we want? The natural vibration period, the TD. Simply, this does not need math. You simply gonna adjust what you're doing here. You're gonna see which, it's up to you. You're gonna just see which peaks are very clear for you. Then they decided to go with this one and that one. They're gonna put down what was the acceleration, function of G, and what was the time. And here they're going to put same thing at the second point. What was the acceleration in T? And then they will, that's what they put in this table. Oops, yeah, that's what they put in this table. And then here to find the time period, simply they subtracted both values from each other and divided it over 10. What's 10? They are the number of cycles we had from here to there. You just need to count them. Just directly count them, how many cycles. And that's it. That's the first answer. Very simple. Then the damping ratio. The damping ratio, we employed this relationship. This one here. This one, which is a function of acceleration. Okay. And yeah, you've got all the levels. So definitely you've got your displacements. And you've got the J. The J is the number of cycles as well, which you can see here. So it's very simple example as a starting example, and we have another one. Any question about what we're really talking about, or it's looking? Yeah, the key thing is you need to understand the actual implementation. Maybe the math for what we want you to do will look simple, but make sure you understand the physical meaning of those parameters and its real implementation in answering real problems. All right. So we have another example. Let's see what else we've got. Okay, so we have a last topic, which is the friction. Okay. By the way, these are the devices I was talking about just before. So these devices would give you more than the 5%. As I said, usually you won't see this one in a city like Melbourne. Maybe in different places you will. This one as well, no. This one may be used at some levels, and they can be hidden in the walls. You don't see them. But we'll talk about this. This is part of our topic relates to how friction can help us to develop a damping mechanism. But this is outside of what we're doing. And maybe we're going to do this section at the start of the workshop. Okay. For now, we just have this example. Okay, so I give you maybe, yeah, it's really kind of very comprehensive. It shows you this is a real structure. You can assume this is a heritage building. Can be many other cases where you can simulate a single degree of freedom system. And you can see what they did here. And based on that, you should be able to report all those properties. Okay. And then do the solution, which I will summarize you about, and maybe we can keep the last topic to run through next week during the first hour. Sorry, not next week, during the workshop. Okay, so for now, let me give you 6 minutes. Yeah, maybe 6 minutes, 3:50, and just read through this, read through the example, and yeah, have a look to what's happening here, but I will summarize it to you again before we end the session at this topic here, the Colombo friction dam system, because I don't want to rush it today. And let me know if you have any questions. All right, we'll see you in 6 about minutes. Okay. Yeah. Any question? Can you answer it? Answer all of them. So simply, guys, to answer such questions, which are key properties for you to work with, and then write your report about how this element is working, is by doing a free vibration test. And what they do there is, as it's written to you here, they gonna use a cable, they're gonna attach it to the tank, right? and they're going to apply a force of 73 kilonewtons, pull the tank horizontally, okay, and then they pulled it up to 51 about millimeters, okay, they measure all that, and then they're going to suddenly cut the cable, and then what's going to happen to your structure is it's going to freely vibrate. And yes, you're going to need to put enough displacement or acceleration sensors that will tell you what's going to happen over the various cycles, when it's starting and when it's ending. From these data, you need to measure and estimate all those parameters. Now, yeah, that's the question for today, but practically what does that mean? You're going to compare those with the original state. You can either use them to start doing dynamic, finding like what we're going to do next week. You're going to find out if there is external cyclic loading, what's going to happen to it, can it withstand it, you know, all that resonance and all these kind of things we talked about before. Solution, you can see, I think I've given you most of the steps. Few of them I ask you to enjoy and continue. And you can see here for question number A, after the damping ratio, and we just had this formula for us already, right? Equation number 1, J, we have 4 cycles that was given to us in the question. Yeah, 4 cycles. Yeah, we had it here. Okay, and J is for the maximum displacement is 50.8. Then later on, when we get to J, it's 25. So we're going to substitute them into equation number 1, and we got this damping ratio. It was 2.76%. The damped natural period, you just total time over the number of cycles. Very easy, you got it there. And we said it's approximately 2 equal to. Can someone tell me why I made this decision? Why I made this decision in saying the natural time period is same as the damped time period? Why I said that? Can someone answer? Well, that's what I'm going to ask you in the final exam. I will ask you maybe a question similar to the one we're doing, but there is always a part which clarify why, or maybe the question can be, can the damped natural period be equivalent to the natural time period, and why? Any answer? Can someone say hi, just to make sure someone is here?
Hello.
Okay, thank you, Silwan.
Sorry, I can't answer that question. Sorry about
No
that.
problem, you don't need to. I just want to make sure my computer is not frozen. That's why it's very quiet. Simply because, what did we say here in this chart? We said if the damping ratio was less than 20%, we can happily assume the difference between Tn and Td is almost 1. Okay, and definitely that's what we found. The damping ratio was only 2%, so it's 0.02 here. It's somewhere very close here. So definitely we can make that assumption, yeah, without any doubt. So that's kind of thing, guys. When you read this, don't just memorize the yes. You may pass the subject or what, but if you want to achieve very well and understand what these skills means as a practicing engineer, you just need to know all these kind of issues. Okay, then we're done with this. Number C, they're asking you for stiffness, because here we did the static test. Stiffness comes from force over displacement. Tick. The natural frequency, we already have the natural time period, and easy, we can calculate it from here. The mass of the water tank, see how we can do many things, many things we can do now. We can even find the mass, which was about 9,100 kilograms. We are able to find the damping, you know, remember I said to you, buildings in Melbourne, they 5%, that's how you can find it from these kind of values as well. So the damping constants, there's a formula I presented to you, and it's all here. The last thing here, it is the I think the last question here, they're asking you for the number of cycles required for the displacement to go not only at 25, but it goes down to 5.1. Simply, you can employ this relationship again. In this case, we already know our damping ratio from here. Yeah, and just calculate for J. It's here. Yeah, so you can see the calculations are really simple, but the idea and the answers, you're going to have a lot of important parameters that will help you to make a judgment about a structure, which you may need to check its health and safety or its situation. Okay, I think that's it for today. I will go through the last topic during the workshop for maybe half an hour plus, and then I will let you work on some examples, and then in the second hour, the workshop, we will continue talking about assessment 1. Okay. Let me stop recording. That will be for